For the second session of today is Volodymyr Takhistov from the Kavli IPMU in Tokyo, who is going to talk about some exciting news about primordial black hole dark matter. So whenever you're ready, we are looking forward to hearing your talk.
Okay. Thank you very much to the organizers for the invitation, and this is a very wonderful workshop. So let me start with briefly mentioning the status of primordial black holes contributing to the dark matter abundance. As you know, there's a variety of constraints, including Hawking operation, microlensing, and gravitational waves, as well as a variety of dynamical constraints, a portion of which is associated with accretion emission. And one particularly interesting region to consider is the region associated with asteroid mass primordial black holes that could contribute to the entirety of the dark matter. Another interesting region is the region around solar masses, where primordial black holes will contribute to gravitational wave signals detected by LIGO. So the standard formation scenario is generally could be summarized as big perturbations entering the horizon and collapsing to black holes. And since you need to arrange for such scenarios to agree with CMB observations on large scales and have a sizable fluctuation on smaller scales that will be collapsing to black holes, such models generically are associated with fine-tuning of the infotone potential. And the corollary of that statement is, of course, that you're quite sensitive to any restrictions in your models and scalar field behavior, for example, associated with the string swampland conjectures. Now, a variety of distinct primordial black hole features are, of course, possible in different scenarios. One particular example is associated with scalar field fragmentation to oscillons, and the idea here is that the inflaton field will be a condensate. It will undergo stochastic fragmentation into localized lumps, and some or dense region could perhaps collapse to primordial black hole. Now, an interesting feature of this scenario is that this could in principle lead to primordial black holes with sizable spin. Another interesting class of models could be the models associated with vacuum bubble multiverse, motivated by multi-field inflation models, and these models will generically produce primordial black holes broadly distributed mass. And this just illustrates that there's a variety of distinct interesting possibilities in primordial black hole features that are feasible depending on the formation model that you consider. Now, of course, since primordial black holes could span many orders of magnitude in mass, there's a variety of very interesting astrophysical observables that are associated with different mass ranges. In particular, tiny primordial black holes, they contribute to the dark matter abundance, and this open parameter space window, which I mentioned at the beginning, could also be associated with production of heavy elements such as gold. As you might know, the origin of heavy elements, such as gold, is a major long-standing problem in astrophysics, and the generic mechanism is the so-called R-process nucleosynthesis, where heavy seed nuclei in a vicinity of many neutrons gets built up to a heavier element. And a very great setting for this is, of course, neutron star mergers. And a big breakthrough in this field has been the 2017 SNS multi-messenger observation. Although some recent studies have been pointing out that perhaps neutron star mergers by themselves might not be enough. And this, of course, has led to some further interest and revisiting of this problem, that as has been picked up by some science media, that perhaps something is raining gold across the universe and no one knows what it is. Now, primordial black holes that are very small can help us with resolving this problem by considering that neutron stars could capture such tiny primordial black holes in dark matter-rich environments, for example, the galactic center, and then the captured tiny primordial black hole would eat the neutron star from the inside, and perhaps in the final stages of this whole system evolution, there will be a sizable emission of neutron-rich material, which would constitute the systems as plausible R-process nucleosynthesis and gold and heavy element factories. And there's a very nice viewpoint highlight on this problem by Hans Thomas Janke. Actually, compact objects, and here I'm also including white dwarfs, are intriguing primordial black hole laboratories more generally beyond just what I described. One can consider the resulting emission to be associated with 511 keV with positrons and the associated 511 keV galactic center axis, and explain it this way. In fact, as a small side comment, you can fully explain the 511 keV using neutron-star mergers by themselves. And there's actually some exciting work happening along this direction, so please stay tuned. But one can also have from such interactions of small primordial black holes with compact objects some novel signatures, such as an orphan kilonova with gravitational waves. And the idea here is that there will be no merger, there is coincidence, for example, like in the case of neutron-star merger. So this would be a novel type of signature that can be thought of and looked at astrophysically related to this scenario. I can also have other signatures such as fast radial bursts, or if there is an accretion disk that forms perhaps a gamma ray burst without gravitational wave emission. One signature that I would like to discuss a little bit more are the so-called transmuted solar mass black holes. And this is just a term that I coined in this study, but this basically denotes solar mass black holes that originate from small primordial black hole or small black hole eating the neutron star. And this brings us to the discussion of the origin of solar mass black holes more broadly. As you might know, solar mass black holes are unexpected in astrophysics due to neutron star stability limit. And for this reason, to a community of people who are studying these kinds of things, this is one of the manifestations, this could be one of the manifestations of primordial black holes. Of course, as I just mentioned, this could also be transmuted black holes associated with small primordial black holes found neutron stars, but also this could arise in models where particle dark matter accumulates in compact objects and collapses. So there's a variety of possibilities. Very intriguingly, LIGO has recently already detected candidate events. So how do we tell their origin? Well, the transmuted black holes which are associated with dark matter, either PBH or particle dark matter eating neutron stars, should follow the neutron star mass distribution, which we know from astrophysics. And just by comparing these distributions on statistical basis, one can already make profound, powerful statements about the nature of dark matter. In particular, that larger solar mass black holes are unlikely to be associated with dark matter interacting and swallowing neutron stars. Now, this brings me then to the discussion of the binary mergers in identifying their origin. Of course, as you probably know, PBH binary mergers have been directly linked with gravitational wave events observed by LIGO, and there is a very large community effort discussing further details and technical aspects of this problem. However, of course, there's another very large class of mergers, black hole neutron star mergers. And LIGO recently reported candidates for these types of events. And could they be associated with primordial black holes? Well, one important conceptual caveat is that unlike PBH mergers, PBH neutron star mergers can only form after star formation. And having studied this in a little bit more detail, one then finds that the combined rates, for example, as seen on this plot right here, integrated from some critical mass of the halo up to the higher masses, one can see that the rates of PBH neutron stars, which is denoted right here, are always subdominant. And what this means is that this leads us to a profound realization that, in fact, the neutron star black hole candidates are astrophysical. They're not primordial in origin. And another interesting comment related to this, perhaps counterintuitive, is that PBH could still be significant because they could come before star formation, even if PBH neutron stars are subdominant. Well, what about intermediate mass black holes? Are they primordial? So this is now going to a higher mass black holes, and LIGO has recently obtained the first definitive detection of intermediate mass black holes. Well, one interesting new general cosmology independent observable is interactions of black holes with surrounding system of gas and the resulting heating of that gas. And conceptually, the idea is quite straightforward, is that when your black hole is within a system of gas, it will interact with the system through a variety of mechanisms, such as dynamic proliferation, gravitational drag, formation of accretion disk and emission of photons, and accretion outflows and winds. And all these are different ways how you can deposit energy in the surrounding system. And then one can consider some favorable systems such as Leo T dwarf galaxy that is dark matter rich, and consider the cooling versus heating balance to place some strong, interesting constraints. Let me also mention that, of course, in this context, it is interesting to also consider formation of jets. And I believe this is the first study that considered jets in the context of primordial black holes. And as you might know, the black holes in general, astrophysical black holes within systems of gas, can generically feature formation of jets. One popular mechanism is the Blanford-Zanaik, and where you have an accretion disk, some magnetic field lines, and they're spun up to form to launch a jet. Now, if that is the case, then with the launching of jet, there will also be a significant sizable cocoon of shocked material that will be spreading out and heating the surrounding gas. Since Blanford-Zanaik mechanism is often associated with spin, this could be a distinct feature for spinning primordial black holes arising from different class of models from non-spinning primordial black holes. In fact, once one goes through the exercise, one finds that one can set very powerful limits or orders of magnitude in mass in primordial black holes. So these would be quite robust limits, including accretion disk emission and winds. And if one considers very efficient jet launching, one can push farther down into the FDM parameter space. But as you can see, you're already spending many orders of magnitude mass with these considerations. Now, once one considers gas heating for these larger black holes associated with interactions with the surrounding gas and the formation of accretion disk and so on, one can also ask what could be the heating of gas from small evaporating primordial black holes using Hawking operation. So this would be a completely different mechanism of heating, but one can also consider this possibility as well. And this brings me to the brief discussion of exploring evaporating primordial black holes with gravitational waves. So as I already mentioned, primordial black holes can span many orders of magnitude and mass with different regimes associated with different astrophysical observables and phenomenological features. However, evaporating primordial black holes below 10 to 9 grams are unconstrained. So the question is how to explore such interesting scenarios where they could appear. Well, one route that people have been considering is the discussion of so-called dark radiation associated with the evaporating PBH emission products, which then could be translated into a change in the relativistic degrees of freedom, delta and F. And what has been recently appreciated by the Fermilab group as well as others is that the spin of the evaporating primordial black hole is very important here. The reason for this is that spinning primordial black holes start to significantly emit in gravitons, and the delta NF can dramatically be modified with spin. Another direction that people have been considering is that production of induced gravitational waves. And the idea here is that when you have a domination of primordial black holes at some stage in the early universe that will then rapidly evaporate, this will be a source of induced gravitational waves, which will later could also be interpreted as a change in delta NF. And here it was appreciated that the mass distribution is very important for primordial black holes because the mass sets the lifetime of the evaporation, and this is the distribution of the lifetime is crucial because you need the rapid evaporation for significant signatures. Now, in the study with collaborators, I have combined these effects and shown that coincident signatures in terms of these effects, as well as gravitational waves, could be used to distinctly probe both distributions of spinning black holes, but also distributions in mass for this region that is unconstrained spinning orders of magnitude of mass. So that is, of course, an interesting possibility, and the upcoming observations will probe this further. Let me summarize that this is a renaissance era in PBH research. Of course, there's a very strong synergy with observational and especially multi-messenger astrophysics. And many new ideas have been emerging recently for primordial hole production, signatures, as well as solutions to old astrophysical, especially astrophysical problems. And I briefly touched upon some of this. And of course, with all of this, we are now trying to understand from different directions what is the role of primordial black holes in physics and its role in the context of dark matter. Thank you very much.
So thank you so much for this very nice talk and review about many different topics on primordial black holes. Let's see if there are questions from the audience. And actually, like I will start fast, quickly. So the first question is about these R processes. Can you a bit talk about how you can distinguish different scenarios of nucleosynthesis in I don't know, core collapse supernovae and primordial black hole neutron star mergers? How can you distinguish what was the main driver? You're muted at the moment.
Yeah, I was scrolling back to the site. Yeah, thank you for the great question, Eduardo. Indeed, this is a very important question, and I know that there are great experts in the audience. Related to this issue. No, thank you. That's a very great question. And indeed, an important question because quite a lot of observables are related to this. So one of the main observables is associated with kilonova. So during a process, you have this emission of elements. They're undergoing a variety of nuclear processes. There's some heating and there's an afterglow. And as you might know, for the neutron star mergers in 2017, various models of kilonova trying to fit in the light curves and the element abundance is one of the key directions that people have been pursuing. So actually, I can already tell you right now that there are some simulations of all these processes that will be happening soon. And hopefully this will answer a little bit more in detail what kind of afterglow can we expect, for example, as one of the signatures. But indeed, this is a very important question, how to distinguish.
And I have a follow-up. And what about gravitational waves from these disruptions? Because I would expect that you have some quadrupole moments, so there should be some gravitational wave signal coming from this disruption. Do you expect to see it, like for example, at LIGO or whatever?
Yeah, this is also a great question, Eduardo. Thank you. So the primordial black hole would mainly settle to the center before it starts to significantly confuse. So in that case, there will be there is not expected significant gravitational wave
Yeah, no, I thought that while setting in the center, it was already disrupting something, giving some quadruple moment or something.
So what you're saying indeed could happen for some parameter space. So if I have a very small primordial black hole, it will not be significant, right? Because I have a big object and a tiny black hole inside. But of course, if I have a sizable object, indeed, what you said would be a significant effect.
Thank you. Thanks for the answer. There is a question by Thomas. Thomas.
Yeah, thank you. Thank you very much for the nice presentation. I think yeah, my comment is partially maybe a question, partially it's indeed additional information to what you said. The fact that the recent kilonova and the R process production, which we think is associated to the kilonova phenomenon, was measured in coincidence with a gravitational wave from an inspiring binary. I mean, this is a clear distinction to the scenario which is connected to primordial black hole nucleosynthesis, right? I mean, I actually do not expect any kilonova detection without gravitational wave measurement, because the kilonova has to be much closer. Do you agree?
I do not have any exact comments on the rates, which I guess is what your question is about, right? The rates and the detectability. So
my question was, or if I want to phrase part of what I said in a question is, wouldn't you, I mean, for the scenario you are proposing, you don't have any coincident characteristic gravitational wave emission, right? You might produce gravitational waves potentially by triaxial deformation, which in a rapidly spinning collapse of a neutron star might happen. But this signature would be distinctively different from the gravitational wave signal which we see from an inspiraling binary.
Indeed.
So we agree.
I agree. Yes.
Okay, good. Thank you.
So you said that there will be no coincident gravitational waves. Indeed, that is the case. So so that's so the point that I wanted to make about this is that this would be a new potential signature that could be looked at. So I think this is summarized here. Orphan kilonovas are gravitational waves.
Thank you. Yeah.
But you're absolutely correct. Thank you.
I mean, if I can add something to Thomas' comment, I think it's also true that in any case you might have like a subdominant contribution to our processes coming from neutron star PBH mergers, and in that case, like that's what you're looking for, like a distinct signal. Because if I understand your comment, it's that basically you expect a different signal in gravitational waves compared to neutron star compact object mergers, for example. So you would say, it cannot be the dominant contribution because otherwise it will be like every time you see like merging, it's like very distinct gravitational wave signal, right?
Yeah.
You might still have like a contribution.
So, right, I see. So you're saying that this could not be dominant. Indeed, you're completely correct. So this is why I wrote it in a precise way that this might not be enough. But you're completely correct. Indeed, this would not be the dominant because we know that neutron stars contribute at least something. Indeed.
Yeah, I mean that's absolutely a viable statement or comment. I mean, as you know, we had one of the talks, I think, in this seminar series or in this meeting, where there was a mentioning that there's a possibility or a discussion about an additional source which adds our process at the very low metallicity conditions into low metallicity stars. I mean, these discussions are going on for quite a while already. Are mergers sufficient to produce all our process, or is there already observational indications of additional sources or an additional source which happens earlier than neutron star mergers could happen? I think we will continue. There will be continuation of this discussion for quite a while, because having observational clues for one source, of course, is never an exclusion of additional contributions. but you must look out for signals which are associated to that source, which are identifiable unambiguously. And that will be the difficult part, I think.
That's a great point. I just want to add that one of the goals of such studies is to perhaps motivate our astrophysics observational friends who are not expecting these perhaps unconventional signatures to also broaden a little bit their horizon. So
yeah,
that's a really good point, actually. Is there any other question from Joachim?
Hi, so thanks for this wonderful talk. I have a question that is not directly related to the R process here, but on the same slide, this primordial black hole inside the neutron star. One thing I've been wondering about how the spin of the neutron star and the spin of the primordial black hole interact with one another, and if that in any way affects the probability for the black hole to explode the neutron star. So for instance, if you have a fast spinning black hole, will it be slowed down by being in the neutron star for a while, or will like the spins of the black hole and the neutron star become equal at some point? How does that interaction work?
That is a great question. So since the primordial black hole in the consideration here is extremely small, the total angular momentum is also quite small in magnitude compared to the angular momentum of the neutron star. So in that sense, I do not expect that there will be a very significant effect. But indeed, the effects of spin and how they interact, and especially will the accretion regime, for example, be modified if you're spinning or not. These are, of course, something that needs to be studied a little bit further, and I hope with detailed simulations, and this will be understood a little bit better.
Do you have a qualitative intuition for whether a spinning black hole accretes more efficiently or less efficiently?
I don't have any particular comments at this moment about this in this system. Yeah.
But it could be an interesting question in a minute. So
indeed,
thanks a lot.
Indeed, thank you.
Thanks a lot again.
There is a I hope a quick question by Andrea.
Yeah, very quick. It's still related also to spin. So you mentioned this scenario of fragmentation in which you can have like big spin, and I ask this also because I'm working on something that requires spin of PBH. So can you have like this scenario for a wide range of masses? So are you able to produce PBH with high spin also for low mass PBH, like that can be kind of dark matter?
Right. So yeah. So that's a great question. So the issue of spinning primordial black holes and their formation mechanisms is right now a topic of ongoing research, and in the context of this model, it is very plausible that this could happen. However, the details of the quantitative distributions have not been studied in detail yet. So this is something that is planned in the future.
And but for example, in this work, even if it is qualitative, which was the target mass of PBH that you had in mind?
Oh, this is a very general framework, so you can have dark matter, you can have LIGO. This is just a general possibility that basically a scalar field can break into pieces. This is the stochastic process, and some overdense region would collapse. So you can either have the n-photon, or you can have a spectator field, and so on.
Okay.
And depending on the pattern.
So sure. I saw that there was a raised hand by Thomas. I don't know if you wanted to.
Yeah, there was. I must say, but I at some point I think I have to do more thinking. This question about a spinning black hole in a more or less more slowly rotating neutron star is an interesting one. There's different aspects to consider. A spinning black hole has a smaller innermost stable circular orbit, but it also has this Kerr metric, which then leads to an interaction of the spins of both. So the question whether it accretes more efficiently or less efficiently is not so easy to answer without a more detailed consideration. I mean, in the end, it shouldn't spin too rapidly initially, because then it will not be able to add more angular momentum. And if it doesn't, if it's not able to add matter because of an angular momentum constraint, it wouldn't swallow the black hole, the neutron star. So there is, I think there's a rich space of possibilities once you consider angular momentum in this primordial black hole.
No, thank you. That's a very
That's
nice set of comments. Thank you.
That's
Yeah,
nice.
thanks a lot to both of you.
So I have to think. I think that I need to thank both the speaker and the audience for interesting comments on these points and on the other topics that Volodymyr described during the talk. And I think that we can move on to the final talk of the workshop.